Hello everyone. In this video we are going to discuss Earth's magnetism. Earlier a little bit of Earth's magnetism we have already discussed, but the fact that when a magnetic needle we take which is able to rotate in a horizontal plane freely, then it always aligns itself in the direction of the Earth's north-south. So why this happens? What exactly is the Earth's magnetic property, that we are going to discuss in this video. So go through the video very properly and see to that if there is any doubt, then post me the doubt after seeing the video. So we are going to discuss here this Earth's magnetism. So let us see how Earth behaves as a magnet. See, here we consider Earth which has a north pole, which is shown by N here, which is called the geographical north, and we have south pole, that is geographical south, which is given by S here. Like if I want to show it by using a pen, then let me show it like this. This is the south pole of the Earth and this is the north pole of the Earth. These are called the geographical north and geographical south pole. And the dotted line here, you can see the dotted line, it represents the geographic axis. Now, when we place a magnetic needle, then we generally see that when we consider a magnetic needle, then the needle is of this shape. Like actually, it looks like this, where the portion here which is marked, which is made dark here, this represents the north pole of the needle and this represents the south pole. If we take an arrow, then this is the north pole of the needle and this one is the south pole of the needle. Now, if such a needle is taken which is free to move in a horizontal plane, and if it is placed in the equator, you can see the equator here. This is the equator of the Earth, as I am marking it. Now in this equator, if we place a magnetic needle which is free to move in the horizontal plane, then what we will see here is the magnetic needle here. Let me take the pen again. The magnetic needle here, you can see, it will align itself in the direction of the north-south, where the magnetic north of the needle, this is the magnetic north of the needle, which will be attracted towards the geographical north. This is the geographical north, but the magnet of the Earth, which is somewhere inside the Earth, that magnet's south has to be here, because of which the magnetic needle's north will be directed towards the south of the Earth's magnet. So you can see here the Earth's magnet, imaginary magnet, this is the magnet of the Earth. It has a south pole which is near to the geographical north pole, the south of the magnet. So this south is represented by S dash and we call it magnetic south. Similarly, we have a magnetic north also here. So we can see here that the freely suspended magnetic needle will align itself in the magnetic pole of the Earth. The magnetic pole, our south pole is here and this is the north pole. So magnetic axis, you can see here, this will be the magnetic axis. This is the magnetic axis which we are drawing here. This magnetic axis and geographic axis, they are not the same. Further, the direction in which we take the north pole, geographic north pole of the magnet, Earth's magnet, the south pole is there. Not exactly there, but a little bit shifted from there. So when we place a magnetic needle, the north of the magnetic needle will be towards the south of the magnetic pole of the earth, and the south of the magnetic pole is very near to the north, that is geographic north, which we generally speak of. So the north pole of the magnet will be directed towards, almost towards the north pole of the earth, that is geographical north of the earth. So I think you can understand this. The freely suspended magnet will have a north pole here. North pole of the freely suspended magnet, and this is the south pole of the freely suspended magnet. So I hope this is clear to you. So here you can see the dotted line shows the geographical axis, and the line which passes through the south and the north. This south and the north of the Earth's magnet, this line will represent the magnetic axis. Now wherever in the Earth you are standing, if a plane passes vertically through the surface of the Earth and coincides with the geographical axis, then it is known as geographical meridian, and if it coincides with the magnetic axis, then it is known as magnetic meridian. So you can say that at a particular point, the geographic meridian and magnetic meridian will not coincide with each other. They will have a certain angle between them. So if they have a certain angle between them, if we place a magnetic needle, so this will be in this direction, but we need to know the direction of geographical north. So we have to know the angle which the magnetic meridian makes with the geographical meridian, and that angle which will be there, that angle will give you the direction of the geographical north. So I think you are clear with the magnetic poles and geographic poles. They are different. Then we have geographic axis and magnetic axis. They are also different. And then we have magnetic meridian and geographic meridian. They are the vertical planes which passes or which includes the magnetic axis and the geographic axis. They are called meridians, magnetic meridian and geographic meridian. So I hope this is clear to you. So here we are having the diagrams and all. So let us see that. The axis of rotation, we have already discussed this geographical axis, then geographic poles, and similarly we have the equators also. We have two equators. This equator which we are the equator which I am showing here now, this is the geographic equator. But you can see here the magnetic axis is a bit tilted. So this will represent the magnetic equator, which is shown by the dotted lines here. So I hope this is very clear to you. So we move to the next part here. Now we have already discussed geographic meridian and magnetic meridian. Now see, when we consider these kind of meridians, the magnetic needle always belongs to the magnetic meridian, because magnetic needle will align itself in the Earth's magnetic poles direction. So this you can see here, this direction. This is the direction in which the freely suspended magnetic needle, which is free to move in the horizontal plane, will stay. So this represents BH. BH represents the horizontal component of the magnetic field. But you know, like when we take a magnetic needle which is free to rotate in the vertical as well as in the horizontal plane, so if it is able to rotate in the vertical plane, then it will actually show the direction. It will actually show the direction in which the magnetic field acts, and which is given by B. And BH, which is the horizontal component of the actual magnetic field B, makes an angle of del with B. BH and B, the angle between them is del, the horizontal component and the actual direction of magnetic field. This angle is known as angle of dip. Whereas the angle which the magnetic meridian makes with the geographic meridian at a particular point, which is given by theta here, this represents the angle of declination. So we need to understand that when you are having a magnetic needle which is free to move in the horizontal plane only, then it will show this direction. But the actual geographical north direction can be obtained if we know the angle of declination. Further, if the magnetic needle is free to move in the vertical plane also, then you will see that the magnetic field, the actual direction of the magnetic field and the horizontal component makes an angle which is given by del, and we call it angle of dip. So I hope that this part is very clear to you. So we move to the next one here. You see this magnetic declination we have already discussed. Then magnetic dip also we have already discussed, given by del. And then horizontal component which is given by BH. These are very important things. You need to understand this. Now see here, we will discuss some of the terms here. See, cos del. This is del here. Angle between the magnetic field. Angle between the magnetic field B and BH. This is del here. So cos of del naturally will be given by BH by B. So BH is given by B cos del. Similarly, for sin del, we can write BV. The vertical component will be given by B sin del. I think this is very clear to you. There should not be any confusion. Now, if we take the Pythagoras theorem or the coordinate system we take, then in that case, what we can see here, if we square them and add them, we will be getting b square cos square del plus b square sin square del, and cos square del plus sin square del, when we will take common, will be equal to 1. So finally we have b is equal to root over bh square plus bv square. Right angle triangle if we consider, and if we want to find the Pythagoras using Pythagoras theorem, we will have the same relation. Okay. Now see, these values can be written here. B, you can see here, root over bh square plus bv square. These are the simple things that you can understand very easily. Now tangent theta, tangent del, tangent of the angle of dip. This tangent of the angle of dip will be actually given by, let me take the pen first. This is the del here, so this line actually represents BV. So tangent del will be opposite side or perpendicular by base, so tangent del will be BV upon BH. So the value of del, that is the angle of dip, can be calculated very easily. Now if we consider the poles, at the poles the horizontal component, if we take a magnetic needle which is free to move in the vertical plane also, then at the poles the angle of dip will be 90 degree. Whereas when we consider the equator, at the equators the angle of dip will be 0 degree. So you need to understand that also. Okay. Now some numericals are there. First question, I will quickly go through the numericals. The vertical component of Earth's magnetic field is given there, root 3 times of the horizontal component. You have to find the angle of dip. Simple formula has to be used and you will get the angle of dip here, which is 60 degree. BV is equal to root 3 BH is given. Tangent of del has to be used. Similarly, a short bar magnet of magnetic dipole moment is given. Calculate the magnitude of the magnetic field produced by the magnet at a distance. This is not included in your syllabus. So I hope that this topic is very clear to you, but still then if you have any doubt, then you can post me the doubt. Okay. Thank you and have a nice day.